So as a practical example in EDA, let's look at verification. Verification is probably the biggest problem that you guys face today if you're designing chips. In other words, a lot of manpower is going to verification. Basically, if you look at the number of bugs that you find in a chip, you find a lot of bugs early in the design, and then it takes forever to find the rest of the bugs, and you're running your compute cycles more and more. So you're running tons of compute cycles. So really you have two phases in verification. The second phase, the later part, where you're running lots and lots of compute cycles, there's really heavy regression activity, and you just need those simulations to go as fast as they possibly can. And your problem is the compute cost, the amount of time it takes, the amount of time it's holding up your project. And the only way to resolve that is to run your simulators faster. Okay, so the industry has solutions for that. In the beginning part, it's really all about setup and debug. There are lots of bugs in your design to find. You need efficient ways to find them. And you need to set up your environment very quickly. The issue there is you're burning a lot of valuable engineering time setting up that environment. So the solution there is verification reuse based on standards and debug automation. So in the first one, in performance, I think the industry, Synopsys, et cetera, has done a very good job making multi-core simulators, emulators, and things like that. We've done well there. In the third one, debug, I think we've done a good job at raising the abstraction in debug, and you should certainly be taking advantage of all of those capabilities. But the standard story really comes in the reuse. The big improvement in verification came when a bunch of techniques about 10 or 15 years ago came out of the processor companies, the Intels, the IBMs of the world. Things like constrained random verification and thing came out, and they started to be used by normal SoC chip design teams. That spurred a lot of innovation. It spurred a bunch of startups. There were companies like E in Israel and Vera, largely over here in India. Those methodologies, those products were adopted. They were, of course, not compatible with each other and things like that, but they offered great promise. Those were then acquired by the larger companies. We bought Vera, Cadence bought E, and we sort of rolled along with that. After a while, the innovation tailed off, and the fact that they're incompatible became a problem. So we standardized it. We created System Verilog, which is now a single standard, interoperable. It's great, very successful standards effort. Once we had the languages, now we created methodologies. How exactly do you use these languages? And we had several. We had VMM, OVM, RVM, ERM, RVM. You can imagine that these are, become a little bit confusing, but in the early stages, they're offering a lot of promise, a lot of innovation. Once they became understood, the innovation tails off a little bit. We were able to successfully standardize those into something called UVM, Unified Verification Methodology. So that's another very, very successful standards effort that's added tremendous benefit to the electronics industry. And then, of course, these things all now sit. We used to get data on a set of standards to get data on and off chip, like PCI Express, USB, DDRs for memories, et cetera. In the old days, getting data in and off chip was fairly random. Now it's standardized. Well, it's good that we have these lower levels of standards like UVM and System Verilog, because if you're trying to verify your PCI Express core, you want to buy a verification IP for that. And you can now if you make sure that that's UVM compliant, written in System Verilog, that will interoperate with verification IP you buy from other companies. It'll go into your system very easily. So it's an example of a tremendously productive standards effort. So we feel very strongly about this. We have been involved in this for many years. I've run the standards activities at Synopsys for 15 years or so, and working for me is a woman named Karen Bartleson, who's been, I think, a very productive member of the industry helping with this. And that was recognized by the IEEE, one of the large standards-making Institute for Electrical and Electronic Engineers, when she was voted this year president of the IEEE Standards Association. So she's the highest standards-making official in the IEEE. And as part of trying to help the industry understand standards and how to create them, Synopsys Press, we published a book by Karen on the 10 Commandments of Effective Standards. And I would just ask, since we spend so much energy in this industry fighting ineffective standards and hope to create good standards, and that is so important to moving the electronics industry forward, and we're not going to get electronics to the masses without effective standards, I would ask people to take I actually brought copies of this, so I have a number of them, and if anybody's interested, I'll give you a copy and I'll send you one if you're not. It's a very even-handed view. The first commandment is collaborate on standards, compete on products. Don't compete on standards. We will not move the industry forward. We will not keep up with the 100 million X improvement in performance. We will not get electronics to the masses, and will not make India sort of the electronics capital that it deserves to be. So my very humble advice for India, and I'm reluctant to even use the word advice for India, is don't start over, leverage existing standards, participate in the development of effective standards if it helps. Don't get drawn into unpredictable standards wars, and just do it, just innovate. India has all the brain power and the entrepreneurs you need to do it. Thank you very much.